Okay, so now we have the two fundamental equations, and that's really all that's needed, right? So let's just write them out. So we have the Friedmann equation like this, and we have energy conservation. And now I wrote out the Hubble parameter instead of A dot divided by 8, but of course that's the same thing. So these are the two fundamental equations that we would need in order to propagate the scale factor forwards or backwards in time. And like I said before, the only thing that we're missing is the equation of state. So let's try and look at some simple examples of the equation of state. How would one go about calculating it? So let's start by perhaps the simplest possibility, namely normal non-relativistic matter, or dark matter if you want, something that is non-relativistic. So we know from classical statistical physics that the kinetic energy density in a gas that is related to pressure, and they're approximately the same. Right, so pressure is 2/3 times the kinetic energy density. And the kinetic energy density, of course, I could write as the average kinetic energy of a particle and then times the number density of a particle. Right, that's kind of trivial, of course. Now, the total energy in a particle we get from the dispersion relation for a free particle, which is given here. And since it's non-relativistic, we should do a series expansion in momentum divided by mass, right? Because that would give us the non-relativistic limit. So the first term, of course, will simply be the mass. That's the rest mass energy. Then the next term will be p squared divided by 2m, which is the normal expression for kinetic energy of a particle in classical mechanics. And then, of course, plus higher order terms. And this is what we normally associate with the kinetic energy in classical physics. This is something that doesn't appear in normal classical mechanics. That's the rest mass energy. But it has, of course, to be counted in the total energy. And that's crucial here. So even though the pressure and the kinetic energy density are similar, the pressure and the total energy density are vastly different. Because we know by assumption here, that's crucial to the whole assumption, right? We know that this must hold true, right? So we know that the kinetic energy term must be very small compared to the rest mass term, because otherwise the system isn't non-relativistic. And of course, the total energy density is given by this expression, which we could then write as the mass term times the number density plus the kinetic energy density, which is this term. But of course now we know that this term is extremely small compared to that term by our non-relativistic approximation, and that means that it's a super good approximation to say that the pressure is comparable to the kinetic energy density, which is way smaller than the total energy density. And therefore, in our language, we don't actually have to care about the pressure of a non-relativistic system because it's negligible compared to the rest mass term. So pressure is unimportant as a source of gravity in general relativity for a non-relativistic particle species. Of course, it's not the same in any way whatsoever as saying that we can always in any system neglect pressure. That's certainly not true, of course. It's not true in a star, it's not true in normal thermodynamics. But in this particular case, we can ignore it as a source term of gravity because it's much smaller than the total energy density. And that leads to a very simple solution to the evolution of energy density, because that means that the energy conservation equation for non-relativistic matter doesn't have the pressure term appearing here. It's just 0. And this equation can be simply integrated. You separate variables, right? So you get rho dot divided by rho equals to minus 3 a dot by a. And then you integrate that, and then you find, because the minus 3, that rho becomes proportional to a to the minus 3. And then you can start thinking about whether or not that's a reasonable thing. And I hope you can quickly decide for yourself that it is, right? Because it's the simplest, most straightforward form of energy conservation. You imagine you have a box and you put particles in that box. Then the total energy in the box, of course, because it resides essentially in the rest mass, is a conserved quantity. So the number of particles essentially determines the total energy. Then you expand the box, and of course the energy density must be proportional to 1 divided by volume of the box. But since the volume is proportional to a to the minus 3, then indeed you get an energy density which is proportional to a to the minus 3. Nothing more. It's completely straightforward. It's the simplest example you can think of. So in a universe containing only non-relativistic matter, or dust as it's usually called in GR, you would always get this behavior. Then the second possibility that is kind of straightforward would be to look at what in cosmology is usually called radiation. Which is just another word for a gas of relativistic particles. So the pressure in such a system, one can calculate, of course. One would calculate it by doing some integral over the particle distribution function. We'll get to this a little bit later. And then you take the distribution function. And then you take, the final thing is, in order to get the pressure, you have to weigh it by p squared divided by 3 times the energy of the particle. And correspondingly, of course, one can do the calculation of the local energy density. And then one gets here the total energy. So each state of the distribution function must be weighed by the energy, of course, of that particular point in phase space. And the same here. And now for a relativistic particle, momentum and energy are equivalent. So you see this just says E, but divided by 3. And in fact, that universally holds true. It's always true for any relativistic gas of particles that the pressure is equal to 1/3 times the energy density. That's completely universal. The only thing that's required is that the distribution function is isotropic in momentum space. That's the only requirement. But that's certainly true if the cosmological principle is fulfilled, right? Because then all directions must be equal. So it's certainly true there. And if the pressure is equal to 1/3 times the energy density, then again, we can solve the equation of energy conservation. Okay. So if I write it out, then I get rho plus 1/3 times rho. So altogether, I get 4/3 here multiplied by 3. So my equation must be this one. So all I change compared to the non-relativistic case is that I now have a 4 instead of a 3. And that means when I integrate it, I find that rho is proportional to a to the minus 4. So again, one might wonder, is that a reasonable thing to get out? And the answer, of course, is yes, fortunately. Because again, think about the box. then the number of particles in that box is a conserved quantity because it expands with the expansion of the universe. So the volume is a to the third. But of course now the energy of each particle is no longer a conserved quantity, right? Because it's not the rest mass, but the momentum that gives its total energy. And since we know from the geodesic equation that the size of momentum is proportional to a to the minus first, that must be the same as saying that energy is proportional to a to the minus first. So each particle loses energy proportional to 1 over a, and that's what gives us this final extra factor of a here. Okay, so that's the two, if you want, simple components that are related to known particles in the standard model, namely, for example, photons and, say, protons, right? One is non-relativistic in the current universe, the other is relativistic. Now we know how they behave. But of course, there might be more to it than just that. In fact, we know there's more to it. We know there's such a thing as dark energy. We also know there's such a thing as the cosmological constant, which is a possible version of dark energy. So if I write it out now, going back to the Einstein equation for just a minute, this is the way we normally write it. And we know that this leads to the Friedmann equation, like this. But in fact, Einstein very quickly discovered that it's possible to put yet another term in the Einstein equation. You can think of this as a boundary term or an integration constant. So in fact, as it turns out, it's possible to put something which is proportional to the metric tensor. So any scalar function, it's in fact related to the stuff that we talked about in the previous video, namely that you have the Ricci scalar appearing here. And of course, you could put any other scalar function in here as long as it's proportional to the metric tensor, because then it transforms properly under any Lorentz transformation you can think of. And Einstein called this the cosmological constant. So let's see, how does that propagate into the Friedmann equation? Well, it turns out if you do this, then you get a term that looks like this. And if you think of this as an energy density of some sort, we haven't specified what it is, right? It's just a constant term. That would correspond to a constant energy density. As the universe expands, the energy density remains constant, which of course is quite weird. Now let's go back and look at the energy conservation equation. So in order to have a constant energy density, I must have rho dot equal to 0. But rho dot can only be 0 if this term vanishes. And this term vanishes if and only if pressure is equal to minus energy density, which is super weird, right? It's a component that has negative pressure. And this is called generically dark energy. And it's been generalized in modern times to include not just this type of equation of state, but rather to write it as some constant W times the energy density, where W is then approximately equal to -1, but not necessarily exactly equal to -1. So dark energy has this type of behavior, and of course now you already know that leads to a roughly constant energy density. So that's the kind of behaviors that we're talking about, right? So we are, just to sum up what we've discussed here, if we have non-relativistic matter, pressure is 0, energy density is proportional to a to the -3. We have radiation. That's pressure equal to a third times the energy density. Energy density becomes proportional to a to the -4. And finally, this thing here, the cosmological constant or dark energy, then we have pressure roughly equal to minus energy density. And that leads to a roughly constant energy density as a function of the expansion of the universe. And of course, not surprisingly, if you plug these solutions into the Friedmann equation, you get different behaviors. So that's the next thing that we should be looking at. That's the classical solutions to the Friedmann equation.